Okay, here we are at section 7.2. This is the next to last section. All right. It's entitled Estimating Mu, once again, like we did in 7.1. However, sigma is not known, sigma being the standard deviation of the population. You don't know it. All right. Focus points learn about what's called degrees of freedom, and what's called the student T distribution. Find critical values using degrees of freedom, which we'll talk about. Compute the confidence interval for mu when sigma is unknown. All right. In reality, to come up with the mean of the population, I'm sorry, to come up with the yeah, to come up with the standard deviation for a population, you have to know the mean. So here he's asking us to find mu, and suspiciously we know sigma. Well, that's kind of crazy. All right, because you'd have to know the mean before you find sigma. So we know something comes after something we don't know. All right, in order to use the normal distribution to find a confidence interval for a population mu, we need to know the value of sigma, the population standard deviation. However, much of the time, when mu is unknown, sigma is unknown as well. If we don't know something about the mean of the population, we certainly don't know about the spread of data around that mean. All right. When we don't know sigma, all right, which is most of the time, we use the sample standard deviation. If you recall, the sample standard deviation is denoted by lowercase s. All right. This approximates the population standard deviation. When we use S to approximate sigma, the sample distribution X bar follows a new distribution. It's called the student's T distribution. All right, so back in the previous section 7.1, we were asked to find confidence intervals. And prior to that, we had to find the error. We subtracted the error from the sample mean X bar on one end, the low end, and we added it on the high end. All right, so this is how we did it back in 7.1. All right, sigma was known. Now, what happens here in section 7.2, we don't know sigma, which is the standard deviation of the whole population. We know the standard deviation of the sample we're taking. Now, that's not the only thing that changes from 7.1. Instead of finding z scores, we're going to be finding what's called t scores. All right, that's where we're going to use this chart. It's called a student distribution. Student distributions were discovered back in 1908 by this guy named W.S. Gossett. He was employed by the Guinness Brewing Company, and the company discouraged publications of research that mentioned the Guinness Brewing Company. As a result, this guy Gossett, W.S. Gossett, he published his work under the pseudonym Student. All right. Gossett was the first to recognize the importance of developing statistical methods for obtaining reliable information from samples of population when sigma was not known. All right, guy's name was Gossett, but he went under the pseudonym. He published under the name Student. So don't get that confused. He wasn't a student. That's just the name he used to publish his work. So the brewing company wouldn't find out about what he did. Gossett used the variable t when he introduced the distribution back in 1908. To this day, and in his on, it's still called the student's t distribution. It might be more fitting to call this distribution Gossett t distribution. However, in mathematical statistics, it's known as the student's t distribution. Okay, all right. So, a couple things have changed. We don't know sigma. We know S now. We don't know the standard deviation of the population. We know S, the standard deviation of the sample. In order to use this student's T distribution, we introduce something called degrees of freedom. And simply stated, the degrees of freedom, DF, is the sample size subtract 1. That's all there is to it. All right, the sample size and subtract 1. Now, let me give you a practical example of degrees of freedom, how it was used, how Gossett used it. We'd have to go back and look at his work and However you use it actually is a little beyond the scope of this course. But anyways, a practical example. Let's assume Brenda's final average in stats is 85 after 4 exams. We can multiply 85 times 4 and determine she scored a total of 340 points. 4 times 85 is 340, or if I take the total number of points, 340, and divide it by 4, there's her average, 85. All right. Using the degrees of freedom, we could assign Brenda any score we want for her first 3 exams. Let's say we said, hey, on the first exam she got a 73, the second exam we got 90, she got a 95, and on the third exam, let's assume maybe she got an 81. We're just guessing. All right. If I total up those 3 scores, she gets a total of 249. Since the total number of points in order to get an 85 average is 340, on her last exam, she has to score 340 minus what she's already scored on the 3. She's got to get a 91 on that last exam. So her total is 340 divided by 4, giving her an average of 85. With 4 exams, the first 3 could have any score we want or any score we determine, any score we guess. But the last score will always be a fixed score. Stated another way, with 4 exams, we have 3 degrees of freedom, meaning we can assign any grade we want to the first 3, but that last one has to be as specific. In this case, it has to total, the sum of the 4 has to total 340. All right, that's an example of degrees of freedom. Now, how it applies to Gossett and how he came up with this distribution, we'd have to go back and actually look at the math that he used. All right, there it is. Degrees of freedom is n subtract 1. We're still finding area under the curve. Instead of using z-scores, we're now using t-scores. Now, back in 7-1, for every confidence level, there was 14 of them, I think, I actually gave you the z-score. I showed you how to do it, but I just flat out gave you. For instance, 95% was 1.96 for a z-score. 99% confidence level was 2.575. I gave you this. Not the case here. You're going to have to find the correct t-score. And how you're going to find it is using that t-distribution that I've told you to download. And here we're talking about, how you actually use the table. It's better if I just show you an example. All right, so at the very top here, you see the area for 1 tail and 2 tail. Ignore this. What you're looking at is this third row. You've got a 50% confidence level, 75%, 80%, 85, 90, 95, 98, 99, and 99 and 99.9. All right. We very rarely use this one. These are the ones primarily, 90, 95, 98 sometimes, and 99. All right, this is the chart. This one here goes from 1 to 22, and then I got 25 all the way through 100. Make sure you have this by your side when you're taking the final, because you're going to use this to find these t-scores, these critical values. All right, so let's assume we want to find the t-value that's associated with a confidence level of 99%, where the end value is 5. So first we find a column with C heading up 0.99. Next, we compute the degrees of freedom. All right, so if n is 5, degrees of freedom is 5 minus 1, or 4. All right, we read down the column under the heading of 0.99 until we reach the row headed by 4 under degrees of freedom. And then we read the value, the t-score in this case here is 4.604. All right, there it is, 99% confidence level, and then there's my degrees of freedom 4. And with this row with this column and this row intersect, we read 4.604. This is what he's saying here. All right, so very important. You need this chart. You need to subtract 1 from n to find the degrees of freedom. Locate your confidence level, and where the two meet. You're in business. All right, once again, back in 7-1, I started you out with calculating the error, and then we actually came up with the interval. I walked you through how to do it pencil and paper, but we found out if you went to stat and test came down to number 7, Z interval, it did it for you. So we start the same way here. We start out by finding the error, and then we eventually take it a step further and we actually find the correct interval. So here's the error formula. We need to know the t-score, S will be given to you, and N will be given to you. So just a matter of entering in those 3 values and letting your calculator do the work. Here's a case where he actually gives you some raw scores. This will happen, all right? Now, in this case here, he takes these raw scores, he finds the sample mean, and he actually calculates the standard deviation. You will not have to do that. When I give you raw scores, there's a way that the calculator does all the work for you. Let's just go on the premise here that we know the standard deviation here, 1.19, and we know X bar is 46.14. We're looking for a 99% confidence interval for mu. All right, we assume that the shoulder heights, the reconstructed, these we're talking about skeletons here from a random sample. All of the information, in other words, I don't give you a problem and somehow the information is not valid and this whole thing doesn't work, all right? The requirements will always be in play. There's no need to even check the requirements. I'm not going to give you a problem that doesn't meet the requirements. All right, so the X distribution is assumed to be a normal distribution. We don't know what sigma is. We will know what S is, and we need to construct this interval. In this case, if N is 7, degrees of freedom is 7 minus 1 or 6. We're looking for a 99% confidence interval. He went to his table, he looked under 99% and degrees of freedom 6. And he came up with a t-score of 3.707. There it is, 99% degrees of freedom 6. Notice this is not N, this is N minus 1 degrees of freedom. Where this column and this row meet, there it is, 3.707. Just what he says here, 3.707. All right, so to calculate the error, in place of my t-score, or my critical value t, which you've got to look up, prior to this, back in 7.1, this was a z-score that I gave you the correct value for. Now you've got to subtract 1, go to a table, find this number. If anything's going to mess you up is you're finding this t-score incorrectly. Either you didn't subtract 1 to find degrees of freedom, or you just flat out looked at the table and came up with the wrong value. S is given to you, the standard deviation of the sample, 1.19. You know what N is. N is 7. All right. Notice this is the N value. This is not degrees of freedom. This is the N. There are seven measurements of these skeletons, whatever. Anyways, your calculator just does the work for you. All right. This times this quotient, 1.67. Now, if I wanted to take it all the way to find a confidence interval, I would take my X bar. This guy should have been on top over here, and that little line should have been on top. Just like back in 7.1, you take the X bar, you subtract the error on the low end, you take the X bar and you add on the high end. All right, and we come up with, we're 99% confident that mu, the mean of the population, falls between 44.5 and 47.5. Once again, you will not have to do this because I want to show you in the next couple of slides. The calculator does it. Now, the majority of time, your calculator will be spot on. There's one exception. When I give you the raw data, the calculator answer and the answer on the answer sheet, there'll be a little discrepancy. In fact, there's one on the homework that's really way off. And I'll talk about that when I do the voiceover for the practice sheet. I will make it such that either it's going to be spot on or it'll be so darn close. I don't want you to have to guess that this one is an A or is it C. I'll make sure your answers are either spot on or they'll be so close, it'll be nothing else even close to it. You'll be able to pick the right answer. I'm not out to hurt anybody or make this more difficult than it has to be. All right, the semester has been challenging. You guys have put a lot of work in this, so hopefully you finish up strong. All right, so the archaeologist is 99% confident that the interval between 44.5 and 47.5 contains the actual population. Meaning, if I took 100 samples, 99 of them would actually contain the true population mean mu. That's what 99% confident means. All right, so there's again, this is the error formula. Now we're using t-scores and we're not using sigma, we're using S. That's what's changed. These two things have changed. All right, so I give you the problems. I give it to you in order. When are you using this formula? When are you using that? Well, you're using this one here when you know what sigma is. Sigma is given to you. When you don't know sigma, you're given S. But they come in order. When you don't see sigma given to you anymore, you'll be given S. So you know to use this formula versus that. This is the one you know when you know sigma. This is the one you use when you know S. And in association with using S, you got to use a T critical value, a T-score, which means you got to go to a table as opposed to back in 7.1 where I just gave you these Z-scores. I gave you 14 of them. All right, so let's start doing some examples here. Suppose X is a mound shaped. We have a random sample of 16 and a mean of 10, a standard deviation of 2. What I've done is highlighted them. And that may be a good idea as you're reading the problem with your pencil. Highlight the end, highlight the mean, highlight the standard deviation. All right, so when you put them into your calculator, you're in business. What I'm going to do here is I'm going to do a pencil and paper, so to speak. I'm looking for a 90% confidence interval. All right, so first thing I know is my degrees of freedom is my sample size of 16, subtract 1, my degrees of freedom is 15. All right, so we're looking for a 90% confidence interval. So there's 90%, 0.900. There's 15 degrees of freedom. You see where those two, the column and the row meet. Your t-score, your critical value, your t-score is 1.753. Well, there it is there. So what I would do if I was doing it pencil and paper, I would take that and I would calculate the error by taking that t-score, multiplying it by S over the square root of n. And once I found what that value was, 0.877, I would subtract it on the low end from the mean, sample mean, and add it on the high end. In doing that, I came up that the mean of the population is between 9.123 and 10.877. I'm 90% confident of that. Now, our calculator will do this. Unlike in the previous section, 7.1 with Z-scores, we are now using T-scores. So I go to stat, I arrow over to test, I come down to number 8 versus going down to only number 7. And once again, the 83 and the 84 are exactly alike. If I'm using T-scores, I'm using the T interval. In other words, if I'm given S instead of sigma, I got to make sure I'm using T-scores. You know, it'd be somewhat difficult if I threw all the problems at you and I mixed them all up. You'd have to be, but I put them in order. I put all the ones using Z first, the ones using T second, 7.1 followed by 7.2. All right, so how do I do this with my calculator? All right, go to stat, I arrow over the test, come down to number 8. Once again, I'm using stats. In other words, stats are, hey, I give you the sample size, I give you the mean and all that. X bar is 10, there it is, the mean is 10. Standard deviation, there it is, 2. Standard deviation, I didn't highlight it, standard deviation is 2. And I tell you is 16. All right, and I took, well, there it is, size is 16N. All right, and we're looking for a 90% confidence level. I hit calculate. Now, what's going to happen is you may think your calculator is broke because it takes a second or two for the calculator to figure it out. So don't get worried. It just takes a little more time than it did with the Z intervals. And here I've got it corrected 3 places. Now, look what my calculator gave me, and look what I just got in the previous slide when I did it pencil and paper. Spot on. Corrected 3 places. That will pretty much always be. If it varies, it's not going to vary by much. Like I say, there's one problem on the homework where the closest one to it wasn't the answer. I didn't know that when I put this together. That I will not do that to you on a test. You'll know it'll be spot on. It'll be so darn close. There's no reason to make a mistake. Now, what it does, it gives you the answer you're looking for. It gives you the interval, and it also gives you back what it told you already. It tells you X bar, it tells you the standard deviation, it tells you how big N was. You knew all this. why it's regurgitating that back to you is beyond me. All right, number 12 here, you have n is equal to 81. The mean is 20. And the sample standard deviation, S, notice it says sample standard deviation, S, is 3. We're looking for a 95% confidence interval. Well, first thing, my degrees of freedom, my sample size and subtract 1, my degrees of freedom are 80. All right, 80's there, and what you can't see, well, you can see it now. There's my 95%. I'm looking for a t-score. My t-score is 1.990. All right, 1.990. Here he's calculating the error. He's calculating the error there. He subtracts it on the low end. He figured it out to be, 0.66. So he took X bar, subtracted 0.66 on the low end, took the X bar, and he added the error 0.66 on the high end. And he came up with this confidence interval between 19.34 and 20.66. Let's do it with a calculator. Once again, you go to stat, arrow over the test, come down to number 8, or just press 8. It's a fast way to get in there. And make sure stats is highlighted. And I give you everything. I tell you X bar is 20. He says, hey, the sample mean is 20. X bar is 20. Standard deviation, the sample standard deviation is 3. There it is. And is 81. There you see it. Confidence interval is 95. I give you, I don't mean to chuckle, I'm sorry. I give you all the information you need to know. All right. It's a matter of putting in 4 numbers, just like in 7-1. All right. So we come up with, notice this, what's the calculator gave us between 19.34 and 20.66, doing a pencil and paper, the previous slide. Spot on. Spot on. There's no need of using pencil and paper. All right. Here's a case where I give you some raw scores. All right. He goes ahead and he actually takes these raw scores. He calculates, he goes to, he puts them into a list and he goes to stat and calculate. And he figures out what X bar is. He figures out, the calculator tells him what standard deviation is. All right. Now, he's really, going through all of this, finding the standard deviation, doing it pencil and paper, because you can see the math here gets really kind of complicated. Not complicated, it's just tedious. Calculating the standard deviation, which we haven't even looked at the formula here. All right. The calculator would give you all this, but we're just doing it everything by hand, which is antiquated. So let's assume, all right, that all we know is the raw data. All right, I'm not going to go in and compute what the standard deviation is, what the X bar is. All I know is raw data. Forget that we even know this, all right? How would I figure out the confidence interval with just given the raw data? Well, what I would go to edit, I'd go to list 1, and I would put in those 2, 4, 6, 8, 9 numbers. You don't see all 9 of them there because the calculator won't show you. They'll show you, 8 at a time? No, 2, 4, 6. It shows you 7 at a time. But you got to realize I put all 9 values into list 1. I go to stat, arrow over the test, come down to number 8. Now, rather than having stats, I've got data. The data meaning these 9 numbers that I entered into a list. All right, where's my data located? L1. So just make sure you if you do these problems, make sure you just always put them in L1. If you put them in another list, you got to remember where the heck you put it, L2 or L3. Frequency, well, the numbers are just used once. There aren't multiple lists. There's only one list, and those numbers are only used once. You're never going to change this. Frequency is always going to be 1. The confidence level we're looking for is a 90% confidence level. You hit enter, and this is one, too, where it takes a little bit of time for the calculator to figure this out, maybe about 2 seconds. But watch what happens. Doing all of this pencil and paper and finding the standard deviation and all this mathematics here. Look what the calculator does. It gives you the same answer you got in the previous slide, doing all that pencil and paper work. Spot on. All right. All you got to do is enter the numbers into a list. Make sure when you go to T interval, you're using data and not stats. Data. You have the raw data here. All right, same kind of problem. I give you 1, 2, 3, 4, 6 different numbers. He's saying use your calculator to verify. No, you don't have to do that. You don't have to do that. All right. Here he does all that pencil and paper, find a standard deviation, yada, yada, yada. Here's what I'm going to do. All right, here are my 7 numbers. Forget all of this is even part of the problem. When you see this on the exam, all we're going to do is give you some raw data and say, hey, find me a confidence interval. I got to tell you what kind of a confidence interval I'm looking for, obviously. All right. So I use list 1. I put in the 7 numbers. 2, 4, 6 is one more missing there. 68, 104, 120, 122, 60, and 64. 1, 2, 3, 4, 5, 6. 1, 2. Yes, only 6 numbers. All right. So stat test number 8. Make sure data is highlighted. If you switch over, make sure you hit enter so this stays highlighted. Where are my values? They're in list 1. There it is, list 1. They're only used once. I'm looking for a 75% confidence interval. Hit calculate. And once again, he gives me the answer spot on, saving me the hassle of doing all of this data. All right, this one here simply wants the error. All right, that's all we want. I don't want the entire interval, but there's a formula for error. I'm looking for a 95% confidence level. My end value is 21. My X bar is 0.16, which will play no part because in finding error, you know, X bar is not part of the error formula. All right, standard deviation of the sample is 0.16. All right, so how to calculate error? It's the t-score. The t-score associated with 95% confidence interval and degrees of freedom 20. If I went to my chart, I found 20 on the left-hand column, and I looked for 95% across the top. Where they would intersect would give me a number of 2.086 for a t-score. S is given to you. S is given to you as 0.16. N is given to you as 21. There it is. All right, so using the formula, here again, I've enclosed this quotient in parentheses. You would not have to do that. You'd have to just put a time sign here. So the parenthesis saves me the time of putting a time sign. So I would just use the parenthesis. All right, then you don't have to use a time sign. Anyways, 0.073, spot on. All right, spot on. All right, a laboratory tested 12 eggs. There's my end value. The mean amount of cholesterol, 225. The sample standard deviation is 15.7. I'm looking for a 95% confidence interval. All right, so stats again, because I'm given stats. I'm given the mean, I'm given S, and so forth. Go to stats, X bar, 225. That's the mean. S, the standard deviation of a sample, 15.7. There it is. Right here, he told me 12. Didn't use a numeral. He spelled it out. And it's still 12. 12 chicken eggs were tested. And 95% is the confidence interval. And there it is, 215.0 on the low end, 235.0 on the high end. Spot on to the correct answer. Letter A. Hope this helps. This is the next to last, and we only got one more dealing with proportion, and we're done. Okay.